Hi guys, welcome to this video on finding the closest approach of two particles. And in this video, we're only going to be looking at it from a purely calculus perspective. So imagine we have two particles, A and B. Initially, A is going to be at 10i and 30j, and B is initially going to be at 40i and 40j. Particle A is traveling in this direction, and particle B is going to be traveling in that direction. So they have position vectors and velocity vectors at time zero defined by this and this. And the first thing we need to do is we're going to find out what the position vectors at time t is going to be of particle A and particle B. So for particle A, all we have to do is we'll take the initial position and then we'll add on the velocity vector after time t, and we'll do the exact same thing for particle B. So that's the initial position of particle B, and this is the direction B is going to be traveling in. So what do we need to do? Well, we know that the distance between the two particles is going to be the length of vector RA minus RB. Okay, because this is the position of vector A, this is the position of particle B, and the modulus represents the distance. So the distance of particle A to particle B is going to be called d. Now, we know what the position vector of A is and the position vector of particle B is. So we can write those out there. So that's the position vector of A, and that's the position vector of B. And what we need to do is we need to subtract those two from each other. And when you do that, you end up with this function over here. Now, we also know that the modulus of a vector, we can use Pythagoras' theorem by taking the sum of the square of each of the components and then square rooting it. So minus 30 plus 7t is the first component, and minus 10 plus 8t is the second component. So when we actually find out what the length is of this vector, we end up with this equation here. So the distance between the two particles is defined by this function at time t. And you can see that that's going to be the first component, that's the x component, and this is going to be the y component. Now, we are going to use a purely calculus perspective for this. This is an optimization problem, and when we want to optimize something, we have to find its derivative and make that derivative equal to 0. So, and when you find the derivative of this function down here, what you'll end up with is this derivative function over here. And we know that we're going to make that equal to 0. So what we end up with is 0 equals all of that. Now, to get rid of the fraction, we'll times all of the stuff on the denominator by 0, which gives us 0, and we're left with that on the top there. And then what we need to do is we need to expand the first bracket, expand out the second bracket, and solve for t. When you do that, you should find that t is 290 over 113. So at time 290 over 113, these two particles are the closest they're going to get to each other. Now we still need to determine what that minimum distance is. So how do we do that? We can use our distance function, which is described below, and we substitute the value of t into that function over there. What does that look like? Well, it looks like this. Looks pretty messy. I'm going to assume that you're going to be using your calculators to help you solve some of these. And we end up with 170 root 113 divided by 113. So that's going to be the minimum distance. And that occurs at time 290 over 113. So now let's look at how we can do that quite quickly with our class pads. What I'm going to do is I'm just going to bring the class pad up. And I've already typed in the actual equation. As you can see over there, I've typed in this equation and it's given us this over here. The way we're going to do this so quickly in our class pads is we're going to go action, calculation, differentiate, and we want to differentiate that with respect to t, and we'll hit the execute button. It gives us all of this. Then we want to solve all of this to equal 0, and when we do that, we need to solve it for time t as well, otherwise it's always looking for the x, and we get t is 290 over 113. Then to find out what the actual minimum distance is, what I'm going to do is I'm just going to copy that function down here, and we're going to simplify this. So we're going to go simplify. We're going to simplify all of that given this bit over here. So we're going to simplify that, given that bit over there. And what we end up with is our 170 root 113 over 13, which is the same as what we had before. Now, in a previous video on the collision of particles and interception of two lines, we looked at a situation towards the end of the video where we had two ships A and B, and we wanted to find out where did those two ships intersect. So this was the position vector of ship A, and this is the position vector of ship B. Ship A started with this coordinate traveling in that direction. Ship B started with this coordinate traveling in this direction. And we did find that the two ships did intersect. Now, we could use this method of the closest approach of two particles to also prove that two particles will collide with each other. And the way we do that is by showing that the minimum distance between the two particles is 0. So that would have been another way to prove that equation. So let's just set it up again. The distance between particle or ship A and ship B is given by this equation. Then we'll write that out fully, and we'll simplify it to this function over here. And we know that this function is the square root of the sum of each of the components squared. So it's the square root of the sum of each of the components squared. Now, this is an optimization problem because we want to find the minimum distance. So we're going to find the derivative. So the derivative, when you plug it into your calculator, will come out with that. But again, make sure you can do these by hand. And we'll make that derivative equal to 0. That gives us this equation over here. Now, obviously, this 8 root 10 doesn't really matter. So we're just solving for t take away 7 equals 0. And that gives us t is 7 over 4. Then, so times 7 over 4, these two particles are the closest they're going to get to each other. Then what we need to do is we need to substitute that into this equation. So when we substitute 7 over 4 into the equation, we'll get the minimum distance is 0. And that's what we expect. So if two particles do collide, we do expect the minimum distance between them to equal 0.